Okay, a couple other things I want to touch on about current electricity, you guys. First thing I want to talk about is this idea of drift velocity, okay? Drift velocity has to do with the motion of electrons through a circuit. We've been visualizing circuitry where I plug wires up to a potential difference and the electrons just flow. Drift velocity is kind of the rate at which they actually move down the wire. And what happens is when you attach a wire to a potential difference, it creates an electric field in that wire. And remember, electric fields exert forces on charged particles. So because there's an electric field, those electrons start to feel a force and they start to move. But the thing is, they don't move just nice and linearly and uniformly because there's a lot of things in their way. There's a lot of atoms and nuclei in their way. So it's more like a pinball machine. Those electrons are bouncing and bouncing and bouncing. And that's what creates heat, is from those collisions. The drift velocity, the actual rate at which the electrons move down the wire, is incredibly slow. It's incredibly slow. It's something like 5/100ths of a millimeter every second, okay? So think about this for a second. When I walk over here and flip on the light switch, that light comes on almost instantaneously. But that's not because the electrons from this switch have made it to that light bulb, okay? Because they're all backed up. Again, it's like the ping pong balls in a tube scenario, right? You have a tube filled with ping pong balls. When I start pushing them in one end, they all start to move, okay? So even though the electrons at this switch have only made it about a centimeter so far, okay, to maybe 2 centimeters now, okay, there's still action happening up there in the light bulb because of the continuous, there's electrons all the way through. So I'm going to draw a picture also of what I'm talking about with drift velocity. So if I hold on a second. So here's a wire. And if I was to look at the electrons in it, they would have random motion, even if there was no potential connected across it. They would just be moving around, and they'd actually be moving around quite rapidly. And they're bouncing all over the place kind of randomly because, that's what electrons do. They're always in motion. I put up a potential difference. I'm going to call negative over here, positive over here. It creates an electric field. Those electrons start to feel a force. And like I said, they don't just go flying through here all of a sudden. Instead, what they do is they still bounce off of lots of things, but now they're generally moving down the wire. And the rate at which they move down the wire is called the drift velocity. Okay, it's much slower than their actual velocity, which is quite frenetic. But as they move down the wire, it's a slow pace, okay, as they kind of work their way down the wire. Okay, now let's look at the next slide. It's killing me. There it is. Picture of the United States. What's wrong with this picture? Okay, this is the United States at night. And notice the world is lit up a lot at night these days. It's the bane of astronomers, and we don't see the night sky much like we used to. Notice particularly, like in Chicago, and, that looks like Denver. We are in a pretty good spot here, but like Southern California, you're hurting. But what do you notice about this picture?
It's like staring at our own galaxy. There's a northeast and we're at
This was a major, major blackout, okay, that happened a few years back. In 2003, actually, it's a long time ago. This was a huge blackout in the Northeast, okay? Our electrical system is interconnected. We have what's called the grid. And the grid transmits electricity to people all over the country, and all over the world is probably very similar. The way our electrical system is set up right now, if things go wrong, it tends to be a big deal. Okay, this is a lot of people in the dark. A lot of people in the dark. And so I want to talk a little bit about kind of how we get electricity from the power plants to the people, because that's what we're trying to do. AC/DC, okay, I know you guys are complaining about the question, but here you go. AC/DC, 2 kinds of electrical current: alternating current, direct current. Direct current is when the electricity tends to flow in one direction down the circuit, okay? And that is what a battery creates. Battery creates direct current electricity. Alternating current, on the other hand, AC, is the kind of current that you get out of an outlet in the wall, and it is oscillating. It's going one way, and then it's going the other way, about 60 times a second here in the United States. We have 60 hertz AC current, and it oscillates around an average of 0, but it goes one way and the other way. And so that's kind of weird. If you think about the electrons in an AC circuit, they're actually not moving down the circuit. They're just oscillating back and forth, back and forth, back and forth, back and forth. Okay? We'll talk more about that when we get into how electricity is generated. But there's a couple of reasons why we use AC. One, the way we generate electricity creates AC current, which is kind of nice. Two, AC current is much more easily transported than DC current. It's very hard to get DC current very long distances, but alternating current, you can do it very easily. Okay, so we diminish the resistance as best we can, but the second thing we do is we try to transmit power at very low currents. Which one's going to have a greater effect on power loss, on heat loss? Current, because you have to square it. So if I can transmit my electricity from the power plant to the people at low current, it's going to have the best effect in terms of minimizing energy loss. You with me? But let's see what's next here. Okay. How do you minimize energy loss? That's what I just talked about. Okay, P equals I squared R. Okay, you minimize power loss by decreasing R or decreasing I, and decreasing I has the greatest effect. But again, we talked about how you decrease the resistance by making the power lines fatter and choosing good materials. And I will have the greatest effect because it's I squared R. Okay? But there's one problem, you guys. There's one problem. If I decrease the current, don't worry about decreasing R, that's not really, doesn't really matter. But if I decrease the current that I'm giving you your electricity, you're getting your power very slowly. Because remember that power equals IV as well, right? Okay, power equals IV. So if I give you power at a very low current, I'm not giving you much power. So you have to increase voltage, okay? So this is why we use high voltage. Because with high voltage power lines, you can make the current very small, but still supply a lot of power to the end user, okay? So this is why we crank up the voltage when we are transmitting power, because basically we're trying to minimize energy loss in the process. So that's why we use high voltage power lines. And when we get into alternating current and magnetic fields and electric generators and transformers and things like that, we'll talk about how we create high voltage and then also bump it back down to low voltage at your house. It's much easier to do when you have alternating current. It's very hard to do with direct current. Okay? Let's talk about the kilowatt hour. We talked about it at the beginning of class. Kilowatt hour is a measurement of energy. Remember, if you want to figure out how much energy something uses, you take power times time, because power is watts, which are joules per second, and then if you multiply that by seconds, you'll end up with joules. Well, a kilowatt is just 1,000 watts, and an hour is just 3,600 seconds. So a kilowatt hour is 1 kilowatt of power being used for 1 hour of time. And we use that unit because the joule is an incredibly small unit of energy, okay? So we buy our energy from the power company in a unit called a kilowatt hour, which is basically 3.6 million joules, okay? That's easy math. I think we did it earlier. It's 1,000 watts times 3,600 seconds. So 1 kilowatt hour is equal to 3.6 million joules of energy. How much do you think it costs here in Colorado on average to buy a kilowatt hour of energy? 10 or 12 cents. It's actually cheaper than that. I think it's usually down around 7 cents a kilowatt hour. If you choose to buy renewable energy from your power company, if you tell them, hey, I want wind or something like that, some power companies will do that for you, but you pay a little bit more, you know, paying 10 or 12 cents. Excellent. Copy's doing that. Okay. Okay, so here's our kilowatt per hour. Again, to give you an idea of power consumption, just some simple appliances that I checked out. Okay, traditional incandescent light bulbs, the ones that you think of when you think of a light bulb that you screw in, those come in 60 watts, 100 watts. 100 was a very common one. 100-watt bulb tends to last for about 750 hours, puts out this much light. Lumens is a measurement of the light intensity. Notice that halogens, a different kind of bulb, 75 watts, a little bit dimmer, lasts a lot longer. Compact fluorescence, which some people are moving to, 14 watts, lasts much, much longer. Comparable light putting out, but for much less power. So again, this is just the way things are going. One of the newest things in terms of lighting people's homes is, they're trying to make LEDs, which are even more efficient than compact fluorescence, last even longer. Right now they're more expensive, however, and there's some other technical difficulties with that. Consider this for a second, though. A 100-watt bulb. Okay, a 100-watt bulb. I have 10 of them in my living room, let's say. I flip on the lights. 10 100-watt bulbs is using a kilowatt of power, right? It's 1,000 watts of power. I leave them on for an hour, 7 cents. I don't have any incentive to turn them off. 7 cents is nothing. Hey, I'll pay 14 cents and leave them on for 2 hours. Okay, so that's kind of why I think we don't tend to think about it a whole lot, because it's really not that expensive for most things. But a compact fluorescent, notice that uses about a fifth of the energy to put out the same amount of light. So one of the reasons why people are going. I just read somewhere the other day that in California, you can no longer purchase 100-watt incandescent bulbs. They are phasing them out of the ability to buy them in the state of California. And they're going to do the same thing with 60 watts and 4 watts, because they're really pushing hard to try to get people to conserve energy. To LEDs. There you go. Craziness. Okay. Typical little radio that you plug in, 15 watts. Okay. Blender 350 watts, starting to use some power. So you want to blend something you want to blend a smoothie for an hour. You've used about a third of a kilowatt hour. Okay, so that's going to cost you, what, 2 cents to blend your smoothie really smooth for an hour. Okay. Okay. It's a good question. And usually it's on there. Most electric appliances will have the wattage on them. A toaster oven. Now, when you get heating elements, where you're using electricity to make heat, it starts to use a lot of energy. So if you wanted to cook your bagel, okay, for an hour, okay, that would be 1.5 kilowatt hours. It would cost you 10 cents, and you'd have a really burnt bagel. Okay, but now we're starting to get up to some consumptive devices. Microwave ovens tend to be on the order of kilowatts. Okay, 1.5 kilowatts. That's my microwave at home, was a 1.5 kilowatt one. Again, if I want to cook my popcorn for an hour, I will have used 1.5 kilowatt hours, okay? And that's, again, about 10 cents. 15 cents if I'm using wind power, okay?